Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over the concept of enthalpy. Now enthalpy is, as the board says, that heat is evolved from a system in a chemical reaction at constant pressure. So this is important for understanding enthalpy. So enthalpy is very specifically defined as the heat evolved, but under special circumstances of constant pressure. So that's important to understand. So that's what we mean by enthalpy. Heat evolved under constant pressure, which is going to be mostly the case because when we're doing chemical reactions, usually the external pressure is the change in the external pressure or the work done by the reaction um, against external pressure is so negligible that we can ignore it. And so I'm just going to go over in this video and kind of define things and show you where we get this idea of enthalpy and the equation to calculate it. All right, so we have to go back to understanding that the delta E of a reaction is the total energy change during the reaction. And what we mean by total energy change, again, is the heat plus the work. And so it's the work that we are usually wanting to ignore because usually it doesn't factor in when we're doing a reaction. We're usually only concerned about the heat evolved or absorbed by the reaction. And so here is kind of a formulaic way of defining the enthalpy, which is noted or symbolized by the capital H. So enthalpy is equal to the internal energy, which is our delta E or E, plus pressure times volume, right? And you recognize pressure times volume from before when we're talking about pressure, volume, work, right? But in the previous video, the volume was kept constant. That was using our bomb calorimeter. And then we had the external pressure. And so using a bomb calorimeter, we were able to keep the volume constant. And so therefore, there was no change in volume, which made zero work. So we were able to focus on the heat evolved from our combustion reaction in a bomb calorimeter. But in this case, we want constant pressure instead of constant volume. And so this is going to be our work. And so you can recognize this equation as, or we can symbolize this equation as H is equal to E plus PV, P times V. And so one of the things you want to recognize is that as we said before, the total internal energy is a state function. And again, let's remind ourselves what a state function is. A state function is a value or a magnitude of some sort that does not depend on how you get to where you're going. How did you get to that state, right? It just depends on what the initial state was and what the final state is. And then you look at the difference between those two states, and that's all that matters. It doesn't matter how you got to that state. The example that I've used before is if you want a chemical reaction to occur, sometimes you will use a catalyst to do that. And the catalyst doesn't affect the beginning and ending state. It just allows you to get from one state to the other state more quickly. You could do the reaction without a catalyst. It will just take longer, but the result is still the same. So when you're trying to find the internal energy, that is a state function. Pressure and volume are state functions. So therefore, enthalpy ends up being a state function. So then when you when you take the change in enthalpy, right? So that during a reaction, you'll have a change in enthalpy, right? So the reactants will have a certain amount of energy to them. The products will have another certain amount of energy to them. And then the change in that is going to be the change in enthalpy. So you have delta H is equal to delta E. Again, that's your change in internal energy plus P times the change in volume. So we're keeping P constant and we're going to change the volume. And so if we remember from before when we talked about pressure volume work, then the external pressure was multiplied by the change in volume, and that was equal to the negative of the work. So the work being done, so depending on how the change in volume goes, right? So if the change in volume is positive, that means this here is going to be a positive value. And so the work being done is being done on the surroundings. So the work is going to end up being negative because the system is going to be losing energy through the form of work. But if delta V is negative, meaning that the final volume is less than the initial volume, then you're going to end up getting a change in volume that's negative. And so that means the work is going to end up being positive because the work is the opposite of what's going on here. So that means that work would be done on the system, and so the system would be receiving energy in the form of work being done on it, right? So that's a quick review of that. So if we take this, we can take this and substitute that in for the equation down here. So if we remember that delta E, the internal energy, is equal to Q plus the work. In this case, we want constant pressure. Last time we wanted constant volume, and so we had Q sub V for constant volume. That's what we represented the heat that's evolved under those conditions as Q sub V. But since we want constant pressure, we're going to change this to Q sub P, right? So the amount of heat from the reaction under constant pressure plus work. And so we have the work here. And so if we take this, we can substitute this for negative work. So if we write this down, we'll substitute this for E. We get delta H, the change in enthalpy. Let me get a different eraser, dry erase marker. So we have the change in enthalpy is going to be equal to, and then instead of delta E, we will have QP plus W. So the heat evolved or absorbed under constant pressure plus work, right? And then plus P delta V. But P delta V is the same as negative work. So then this becomes Q sub P plus work minus work. And as you can see, the work cancels out. So work is no longer a factor. So here we have delta H. The change in enthalpy is going to be equal to the heat evolved or absorbed under constant pressure. So this is what is important for us. So as you can see, under constant pressure, enthalpy ends up, the change in enthalpy ends up being the Q value under constant pressure. Okay, I hope that's clear. The last thing I want to talk about is this idea of endothermic reactions and exothermic reactions. And this is tied to this change in enthalpy. So remember, change in enthalpy is going to be, enthalpy is like a state reaction, a state function. So the change in enthalpy is just going to be the final enthalpy of the reaction minus the initial enthalpy. So these two states, final minus initial, is going to give you that amount. And so, so if we go back to our energy diagram, right? So we have maybe we have reactants up here, and we have products down here. So you start with higher energy, and so maybe this is enthalpy. And so maybe the reactants start with a higher amount of energy, and the products you get are lower energy. So you're going from high to low, excuse the noise there. So in that case, you're going from high to low. So final minus initial. The final is low minus the initial, which is high. So here, your delta H will be negative, right? So in that case, if you have a negative enthalpy, you're losing energy. The reaction is losing energy. And so energy is going out of the system because the reaction is always going to be the system. I shouldn't say always, but many, many times we're going to be interested in the reaction as the system. And so if we have a negative change in enthalpy, that means the system is losing that energy. And so that's what we would call exothermic. So an exothermic reaction is one where the delta H is negative. Now, you can remember exothermic. Therm is the root of the Greek for heat. So you can remember that by thermometer. So thermometer is the measuring tool for measuring heat. You have a thermos. So a thermos is a container that keeps heat in. If you want to keep the soup, like if you have hot soup, you want to keep it warm. So it'll keep the heat in, or if you want to keep something cold, it'll keep the heat out. So you call it a thermos, right? So therm refers to heat. Exo means going out of, right? So going out of. So the heat is going out of the reaction. So it is an exothermic reaction. So it's negative because it's losing that heat because it's going out. If it goes the other way, if instead of reactants we have products on top, right, and we have reactants on the bottom, then we'll be going from low energy to high, and in that case the delta H is going to be positive. And so that's an increase in energy. So the system is receiving energy, receiving heat. And so that would be an endothermic. Endo referring going into. So the energy, the heat, the therm is going into the reaction or into the system. So in this case, delta H is going to be positive. So that's what we mean by exothermic and endothermic reactions. You might also hear the terms endergonic and exogonic reactions as well. But I'll be using mainly endothermic and exothermic to refer to reactions or systems that are losing or gaining heat. I hope this is helpful. If you have any questions, please make a comment in the comment section. Let me know what you think. Is there anything else you want me to go over? I can make videos on other things based on what people are asking for. If you like this video, share this video, hit the notification bell so that way you can be notified of any future videos I put out. Make sure you subscribe to the channel, and again, make a comment in the comment section. Let me know what you think. Thanks for joining me, and I'll see you next time.